Hello. So this is lecture 5 of the series Special Theory of Relativity, and the topic of this lecture is length contraction. So let us start with the topic. Before moving towards length contraction, let us revise a little bit about time dilation, which we covered in the last video. So I can summarize time dilation in one statement as follows. Every clock runs the fastest in its own rest frame, which means that if there is an observer and the clock is moving with some relative velocity u with respect to that observer, the observer will see that the clock has slowed down by certain amount. So in any other frame of reference where the clock has some velocity, it slows down, which means that its time period is increased. Okay, now moving towards length contraction, let us first give a formal definition. Length contraction is a phenomenon that a moving object's length is measured to be shorter than its proper length, which means that if I see an object and that object is moving relative to me, it will appear to be shorter than its original length. Okay, original length over here means a proper length. So let us define proper length. Length of the object in its rest frame is called as proper length. Okay, now let us understand this length contraction by doing a thought experiment. So in this thought experiment we need two observers, so let the two observers be you and me, and we both buy identical meter sticks from the shop. And in this thought experiment later we can conclude that once we start moving relative to each other, our meter sticks don't agree. So let us see why do they don't agree. Okay, now as the meter sticks appear to be shortened, or an object appears to be shortened, there must be a factor by which they are shortened, and that factor is reciprocal of our Lorentz factor, and our Lorentz factor is nothing but gamma. Therefore 1 over gamma is the shortening factor, which comes out to be under root 1 minus u square by c square. Okay, now what happens in this thought experiment is that I stand on the platform holding my meter stick and you board a train holding your meter stick. And once you board the train, I argue that your meter sticks are shorter. So let us see how they are shortened. So as we have a thought experiment and we have two observers, therefore we need two frames of reference to compare their observations. So here is the S frame and S prime frame, and I am in the S frame and you are in the S prime frame. So this S frame is the rest frame of the rod, which means that in this frame the rod is at rest, and as I am in this frame and the rod is also, and this is the rest frame of the rod, I'll measure the proper length of the rod, and that proper length is nothing but, let's say, L naught. And you are in this S prime frame which is moving to the right with the relative velocity u. So for me when I see your meter stick, it appears to be shortened. So let us see how. Okay, now in the context of special theory of relativity, as I have said earlier, that it always becomes easy to understand a concept when we divide that concept into two set of events. So let us divide this measuring activity into two set of events. So first event is front end hits a marking. So this is the front end and it hits a marking, let's say L. Okay, and event 2 is the back end hits the origin. So this is the back end and it hits the origin. Okay, now there is only one condition, that the measurements have to be simultaneous, which means that the activity of seeing this front end when it hits the marking L on this graduated scale, and when this back end hits the origin on this graduated scale, the observation of these two events have to be at same time. This is the condition because when we are measuring the lengths on a graduated scale, we can measure the length of the object only when front end of that object and the rear end of that object hit the marking at the same time. if we observe them at two different times, we are obviously not measuring the length of the object. So let us move further. Now we are using over here the inverse Lorentz transformation for the differences. So del x is the spatial difference between the two events in the S frame. Del x prime is the spatial difference between the two events in the S prime frame, and del t prime is the time difference between the two events in S prime frame. And here is the relation which we have for differences in Lorentz transformation. If you don't know about this relation, I'll post the link in description of lecture 2 and you can learn about it. Okay, so del x, I can say that it is the length of the rod according to the observer who is in the rest frame of the rod. Okay, so this is the rest frame of the rod and I can say that this is del x, the this event of observing front end at L0 and the rear end at origin. I can say that the difference between spatial differences between these two events is del x, okay, which is equal to L0. Similarly, del x prime can be said to be the length of the rod according to the observer, who is in S prime frame moving with relative velocity u with respect to S frame, and del t prime is the time difference according to the observer who is in S prime frame. Now, as a person who is in the S prime frame, when we are sorry, not a person who is in the S prime frame, when we are measuring the lengths in the S prime frame, obviously as the events have to be, the measurement events or the observing events have to be simultaneous, we have del t prime is equal to 0, and therefore we have L naught is equal to L over under root 1 minus u square by c square. Now rearranging these terms, we get L is equal to L naught times under root 1 minus u square by c square. Now this factor under root 1 minus u square by c square is lesser than 1, and therefore we have L is less than L naught. Okay, so this is the shortening of the length for your stick as I observe. Thus, I claim that your meter stick when you board the train is shorter than mine. Similarly, you can also stand on the platform and I can board the train, and at that time you can claim that my meter stick is shorter than yours. Okay, or even though when you are in train, you can see me, if I can see you moving towards right, you can see me moving towards left, and you can say that you are stationary and I am moving, and therefore you can also claim that my meter stick is shorter than yours. Okay, now this was all about length contraction for this lecture. I can summarize length contraction and time dilation in two simple statements. Rod appears longest in its rest frame, which means that if I am in the rest frame of the rod, it will have some length, proper length L naught, and when the rod is moving relative to me, it will appear to be shortened than its proper length. Now, similarly, we can say for time dilation also. You can learn about time dilation in lecture 4. I'll post the link in the description. Uh, for time dilation, we can say that clocks appear fastest in their rest frame. Clocks appear fastest in their rest frame, which means that if I am in the rest frame of the clock, it will have some time period, say tau, and if the clock is moving relative to me, then that clock will appear to be slowed down, which means that it will have some time period t which is greater than tau. Okay, so this was all about length contraction and a little bit summarizing about length contraction and time dilation. So thank you.